In this lesson, we will be working on simplifying trigonometric expressions as well as establishing trigonometric identities. We get started by just simplifying expressions. So in these first sets of examples, they give us a trigonometric expression. Notice that there's no equal sign in this. They just give us this expression and they want us to simplify it. Later in this lesson, when we are verifying trig identities, you'll notice that we will have an equal sign, and it'll be our job to prove that these two sides are equal. So just starting with simplifying expressions, we use the same identities that we've seen before. So these identities should look familiar. Back in Unit 1, we had several problems where I would give you a trig function and ask you to use these identities to find other trig functions. Now we're going to use these identities to simplify trig expressions. So getting started in number 1, one technique that we will use in this lesson when we have an expression that has various trig functions in it, one thing we will do is we will start off and we will rewrite the expression with only sine and cosine. So if I want to rewrite this with only sine and cosine, I don't want to write cosecant anymore because that is not sine or cosine. I will replace that cosecant with 1 over sine x. The cosine squared, the second factor, I'll leave that as it is because it's already in terms of cosine. And then the secant x, I'm going to rewrite as 1 over cosine x. And now we'll work on just simplifying this. We multiply fractions straight across the top, straight across the bottom. This cosine squared in the middle is a cosine squared x over 1. So in the numerator, we have 1 times cosine squared times 1, which is cosine squared. And in the denominator, we have sine x times cosine x. We can, of course, cancel one of these cosines. We can cancel with one of the cosines in the top. So the cosine in the top is no longer squared. In the denominator, we have sine x still there. But we were told that we want the final form with no fractions. So I don't want to leave this fractional answer of cosine over sine. I'm going to go back up to my identities and see that cosine over sine is equal to cotangent x as our final answer for simplifying that trig expression. We'll do the same thing in number 2. I'm going to rewrite this in terms of only sine and cosine. So in the numerator, I'll keep the cosine squared the same. In the denominator, I'll keep the sine x the same. But then the cotangent x that shows up in the denominator, we're going to replace with cosine x over sine x. So keep in mind, we do have fractions within fractions in this example. So in the numerator, we only have a cosine squared x. And then in the denominator, I'm going to multiply these fractions and see that the sine x will cancel and only leave us with the cosine x in the denominator. And then with the cosine squared over a cosine, we can cancel one of those cosines and be left with only cosine x as our answer for number 2. We're going to start number 3 off the same way using our fundamental identities. I want to rewrite this expression so that we only have sine and cosine. In the numerator, we have a secant squared, and I'm going to use the reciprocal identity that secant is 1 over cosine to replace the secant squared with 1 over cosine squared. In the denominator, we have a tangent squared. We'll use a quotient identity to replace that with sine squared over cosine squared. And again, remember, for instance, the identity in green, the tan squared, I don't want to use the fact that tangent is 1 over cotangent because remember that my goal right now is to write everything with only sine and cosine. So I didn't choose the 1 over cotangent because I want to see sine and I want to see cosine. So I brought down my minus 1 that was there. Let's keep simplifying this. In the first term, we have division of fractions. So we will simplify that by multiplying by the reciprocal. Keep, change, flip. So I kept the initial fraction of 1 over cosine squared the same, and I flipped the fraction in the denominator. Now we can see that the cosine squareds will cancel, leaving us with 1 over sine squared x minus 1. I don't want any final fractions in my answer, and 1 over sine squared is equal to cosecant squared, because cosecant is 1 over sine. So we have cosecant squared x minus 1. And yes, we are at a point where we no longer have fractions in, so we have simplified this, but this can simplify a little bit further. One thing you're going to notice in this lesson is that when you get to a point where you have a squared trig function and a 1 showing up, you should be thinking about Pythagorean identities. Because you'll notice the Pythagorean identity that I highlighted in green, if I were to manipulate this identity, we could see that cosecant squared x minus 1, so if I subtract 1 from both sides of this identity, cosecant squared minus 1 is equal to cotangent squared x. So this final answer that we have here, I'm not going to leave as cosecant squared minus 1. I'm going to change it to cotangent squared x. Here in our fourth example, we again want to simplify this trig expression. Typically in the first 3 examples, we've started off and converted things to sine and cosine. I want to show you why that does not work in this example here. If I were to change things to sine and cosine, I would leave the cosine the same. I'm going to rewrite that just so my fractions are aligned. The 1 over cosecant squared I would replace with 1 over sine squared. I'll leave that cosine alone. I'll leave this cosine alone. 1 over cosecant is 1 over sine, and then I'll leave the cosine. And at this point, this is not very helpful because notice nothing is canceling out in here, right? I hope no one is thinking that like we can just cancel those 2 cosines right there, because in a fraction, all of the factors need to have that. All of the terms need that factor in order to cancel. So I couldn't just cancel 2 cosines, but I hope you do notice that every single term in this expression has a cosine that shows up in it. So since cosine shows up in every term in the numerator, we can factor cosine out. And since cosine shows up in every term in the denominator, we can factor cosine out. When we factor cosine out of the numerator, we're left with a cosecant squared x minus 1. Because when you factor something out from itself, you're left with a 1. When we factor cosine out in the denominator, we're left with a cosecant x plus 1. Now, I can cancel these cosines and be left with cosecant squared x minus 1 over cosecant x plus 1. And we still have a fraction, so we're not done simplifying this. I do want to mention something about the expression in the numerator, because we had just said that if we see squared trig functions and 1s that we could use a Pythagorean identity. So I could understand the urge to replace this numerator with cotangent squared. This is not what we're going to do, but I want to explain why. This is correct, technically, but it doesn't help us simplify this expression because I can't cancel anything out in here. So I would not do this. Instead, we need to observe that the numerator is a difference of squares. The numerator looks like a squared minus b squared, which always factors into a plus b, a minus b. Now let's say that we don't see that. Another technique that we'll discuss is when we're simplifying trig expressions and we get to a point where we only have one trig function, like I only have cosecant showing up in this expression now. One thing you'll see me do throughout this whole unit is I'll introduce a new variable and I'll say, okay, let's let p be the only trig function we have, which is cosecant. So that means now when I rewrite this, I wouldn't write cosecant squared, I would just put p squared. And then I still have minus 1. And in the denominator, I wouldn't put cosecant plus 1, I'd put p plus 1. Now this looks something a lot more algebraic, very much so from 171, where hopefully we can factor the quadratic in the numerator. We're looking for 2 numbers that multiply to -1 and add up to 0, and those numbers are positive 1 and negative 1. So notice here, I have just completed my factors of that difference of squares. And now I can see that the p plus 1 would cancel out and just leave me with p minus 1. Now I'm not going to leave my answer in terms of p, because remember we had let p be cosecant. So I did all of this to show that what you would really want to do here, instead of applying that Pythagorean identity, is you would want to factor the numerator into a difference of squares as cosecant x plus 1, cosecant x minus 1, then you see that the cosecant x plus 1 in the denominator can cancel the same way our p plus 1's canceled and leave us with simply cosecant x minus 1 as our final answer. So a couple of things I want to point out about this problem is as we work through this lesson, we are going to have to be comfortable identifying expressions that look like this here, as a difference of squares. So we should be able to factor these trig expressions that look like that, a squared minus b squared, into a difference of squares, especially if we're seeing something like cosecant x plus 1 showing up in the denominator. Another thing I want to mention is this final answer down here, we cannot use a Pythagorean identity on that. So I know earlier we said we need to watch out for squared trig functions and expressions with a 1 in them here, but this is not squared. So please don't think you can turn that into cotangent squared x, because it's not. So we can't use a Pythagorean identity there. We now move on to our second objective, where we are going to be working on verifying identities. So what that means is I'm going to give you an equality, and it's going to be our job to prove that these two expressions on the left side and on the right side are equal. Generally speaking, I'm going to suggest that you start with the more complicated side and simplify that down to show that it's equal to the more simple side. So we are going to start off with the left side of this expression, which is cosine negative x, secant negative x, plus tan negative x, multiplied by cosecant negative x. And we want to simplify this down to show that this is equal to secant plus 1. So first thing I'm going to do before I start switching things to sine and cosine is I'm going to get rid of all these minus x's that are on the inside of those trig functions. And the way we do that is we're going to use even and odd identities. So for example, I can see that cosine of negative x is the same thing as just cosine x, because cosine is an even function. Secant of negative x is the same thing as secant x, because secant is also an even function. Tangent, however, is an odd function. So tangent negative x is negative tan x. And then cosecant is also an odd function. So cosecant negative x is negative cosecant x. So now let's just work on simplifying these minus signs that we have in here. We have cosine times secant plus, we have a negative and a negative, so they'll cancel out and just leave us with tangent times cosecant. And now we're going to continue simplifying this. So I'm just going to rewrite this expression. And I'm going to start switching things to sine and cosine now to simplify them. So the cosine I will leave alone since it's already a cosine. The secant I'm going to replace with 1 over cosine. The tangent I'm going to replace with sine over cosine. And the cosecant I'm going to replace with 1 over sine. And now let's see if anything cancels. So we do cancel out a cosine, which leaves us with a 1 in the first term. And then we cancel out a sine, which leaves us with, now let's multiply fractions straight across the top. 1 times 1 is 1, straight across the bottom. Cosine times 1 is cosine. So we have 1 plus 1 over cosine. And we know that 1 over cosine is secant. And so we're left with 1 plus secant x, which is the right side of that equation. Because secant x plus 1 and 1 plus secant are the same thing. So all of this work of us starting with the left side of this identity and doing all of these identities to arrive at the right side of this identity have verified that this equation is in fact an identity. So your work for problems like this is using the identities to get to the other side. I'm going to start example 6 the same way with the more complicated side, which is the left side of this identity. And before we go any further, I would like to point out that I want to be clear that in number 5, these minuses on the inside and here are our indication that we should start off and use even odd identities with all those minuses on the inside. After we used even and odd identities and we had no more minuses on the inside, then we were ready to switch to sine and cosine. Because the thing about this lesson is you're going to have to know what techniques to use in order to establish these identities. So because we're going to use a different technique here in number 6. Here in number 6, I've started with the left side. It was more complicated. I'm trying to show this is equal to 2 tan x. I noticed that the left side has 2 terms. They're both fractions. I'm trying to show that this is equal to 1 term. So I'm going to start off and I'm going to look for a common denominator. I'm going to write the difference of these fractions as just simply one big fraction. So to do that, our common denominator will be the product of the 2 denominators. So we're going to rewrite the first fraction with a denominator of secant x minus tan x multiplied by secant x plus tan x. I'm doing that to the first fraction. The first fraction already had a 1 in the top, but it did not have this secant x plus tan x, and so I'm going to need to put a secant x plus tan x in the top. If I put that in the top and multiply it by 1, I'll just see secant x plus tan x. So far, all of this is just that first fraction. You can see that what I have underlined in green technically cancels out. I do not want to cancel it. I'm trying to get a common denominator, but just showing that I have not changed the problem. Now let's go on to do the second fraction. The second fraction had a 1 in the top and a secant x plus tan in the bottom. I'm going to write the secant x plus tan over here. Not that it matters. So this was the first fraction originally. The common denominator means I need to add a factor in the bottom, multiply a factor in the bottom of secant x minus tan x. That was not already there, so I'm also going to multiply it in the top with the 1 that was there. So I just took the 1 away, and this is what I have. So everything circled in green is everything circled in green. Because you can see what's underlined in blue technically cancels and leaves us with the original expression. So now we have a common denominator and we can combine all of this into one big fraction where the denominator will be the product of secant x minus tan x multiplied with secant x plus tan x. We're going to combine these numerators. In green we had secant x plus tan x, and then in blue, be careful here because we have a minus sign going to the secant to give us minus secant x, and we have a minus sign going to the tangent to give us plus tan x. So when we distribute that negative, we can see that these secants cancel out, and in the numerator, we're left with tan x plus tan x, which is 2 tan x, and in the denominator, we're left with the product of secant plus tangent, secant minus tangent. Remember, we're trying to show that all of this is equal to 2 tan x, which we do have in the top, so hopefully we can show that the bottom is equal to 1. Maybe you notice that the bottom looks like a plus b, a minus b, and when we multiply that out, we get a squared minus b squared. We just talked about that from a difference of squares, or even if you don't observe that pattern, when you FOIL out the denominator, you will get a secant squared minus a tangent squared. We see squared trig functions. I'm thinking of a Pythagorean identity, especially since I know I want the denominator to equal 1. And when I look at this identity here, if tangent squared plus 1 is equal to secant squared, then secant squared minus tan squared is equal to 1. And I see that by just subtracting tan squared from both sides of this identity. So now I can use a Pythagorean identity to replace the denominator with 1. So from there to that 1, that's a Pythagorean identity. And I'm left with 2 tan x as my final answer, which is the right-hand side. I don't need to necessarily box that in, but just showing that we did get what we wanted from the right side of this identity establishes it. I'm going to start example 7 with the more complicated side. The fraction of cosine x divided by secant x plus tan x. I'm trying to show that that's equal to 1 minus sine x. I'm going to switch to sine and cosine. So I'm going to leave the numerator of cosine x the same. The denominator with the secant x, I will replace using a reciprocal identity. And the denominator with the tangent x, I will replace using a quotient identity. So now we have this expression here. Nothing has canceled out, doesn't necessarily look simplified. However, I want to get rid of these fractions within the fraction. I have these fractions in the denominator with the cosines in them, in their denominators. So what I'm going to do is I'm going to come into this fraction and I'm going to multiply everything in this fraction by cosine. So I'm essentially coming in and I am choosing to multiply this fraction by cosine x over cosine x. Notice that this is just equal to 1, so I'm not changing anything. So I will have to distribute the cosine x to the cosine x that's in the numerator already, which will give us cosine squared. And then the cosine x in the denominator gets distributed to the 1 over cosine, which would cancel and leave us with a 1. And then the cosine x gets distributed to the sine over cosine in the denominator. The cosines will cancel and leave us with a sine x. So this is what we have here. Now this still does not look like the right-hand side, which is 1 minus sine. But again, thinking about difference of squares, this kind of looks like a difference of squares factor, and this kind of looks like a difference of squares factor, like the a plus b, a minus b. However, in the numerator, we just have a cosine squared. So what I'm going to do is I'm going to apply a Pythagorean identity to the numerator, because cosine squared is equal to 1 minus sine squared x. A denominator is still 1 plus sine, but what using that Pythagorean identity does for me is it allows me to now factor the numerator as a difference of squares, because 1 minus sine squared factors into 1 plus sine, 1 minus sine, and then I can cancel the factor of 1 plus sine that shows up and be left with the right-hand side, which is simply 1 minus sine, which establishes that identity. So again, we're seeing these themes show up where we think about what we're trying to get to, what we already had. Seeing those two things that are highlighted in yellow is really what sets me off to say, I want to change this cosine squared using a Pythagorean identity to 1 minus sine squared so that I can be able to factor the difference of squares, and then I can cancel out and be left with 1 minus sine x. In example 8, I don't know that I would say one of these sides is necessarily more complicated than the other. It doesn't really matter in this case which side we start with. In either case, we're going to have to use the same technique. So let's get into that. When I look at the right-hand side of what I'm trying to get to, I notice that there's a cosecant x plus 1 that shows up, and that kind of sets me off because these two together make up the factors for a difference of squares. And then I also notice that I have a cotangent showing up in this expression, and what's interesting about that is that cosecant and cotangent are the pair of functions that show up together in a Pythagorean identity. So I'm just observing that, hey, I have cosecant and I have cotangent in my expression, and there just so happens to be a Pythagorean identity that involves the two of them. I also, like I mentioned earlier, this is one of the factors for a difference of squares. So to take advantage of that, what I'm going to do is I'm going to come in and multiply and divide both sides of this expression by cosecant x plus 1. So everything I've written in blue still equals 1, that entire fraction. But the reason that I choose that is because now when I multiply these fractions in the numerator, I'm not even going to distribute. I'm going to leave that like that. But in the denominator, now I have this cosecant x times cosecant x minus 1 times cosecant x plus 1. That is a difference of squares, which would multiply out to be a squared minus b squared, cosecant squared minus 1. So I've just multiplied out the denominator. I want to speak for a second on why I'm not going to distribute the cotangent in the numerator. I'm not going to do that. I'm just going to leave the numerator as cotangent x times cosecant x plus 1. And the reason that I'm doing that is because this cosecant x plus 1 shows up right there. So I don't want to distribute that cotangent now. I want to try to preserve that because it's getting me closer to what I want to have on the right-hand side of this identity. So I'll just copy over what we have so far. We introduced that text in blue. We introduced this so that we could have the difference of squares in the bottom to get that. Now, what are we going to do with this? We're going to apply a Pythagorean identity because we did observe that already. Now we have a squared trig function with a 1. Cosecant squared minus 1, looking at this identity here, suggests that cosecant squared minus 1 is equal to cotangent squared x. So I'm going to replace this denominator with a cotangent squared x. Then I can cancel a cotangent and be left with the right side that we were trying to get to, which is cosecant x plus 1 divided by cotangent x. And that establishes that identity. In example 9, we have all of these natural logs showing up. Notice that some of them are subtracting and some of them are adding. I'm going to remind us of our rules of for logarithms from 171. We had rules that said like log A minus log B was the quotient rule, which is log A over B. We also had a product rule that says log A plus log B is log AB. So when we have two logarithms that are being subtracted, we condense them into a single logarithm, and on the inside of that logarithm we have division. So I'll take the sine and divide it by the cosine. If you wanted to put the absolute value bars individually, you could, but that is the same thing as this. So this is divided because of this minus sign, using the quotient rule for logarithms. Then we add in a log with a cosecant on the inside. So since we're adding, we're just going to multiply the absolute value of that cosecant with that. So far, all of this is inside natural log. This is the left side. So just to be clear, how I got from here to here, I'm using rules of logarithms from 171. I'm using rules of logarithms from 171. So now let's just simplify what we have here. We have natural log, and on the inside of that natural log, an absolute value. I can just multiply all of this stuff together. Sine times cosecant divided by cosine. Well, let's switch to sine and cosine because then it will be very easy for us to see that the sine will cancel because I replaced the cosecant x with 1 over sine using a reciprocal identity. So I cancel that sine out and I'm left with natural log of the absolute value of 1 over cosine, and 1 over cosine is secant. So we have established this identity because we did get natural log absolute value of secant x. In example 10, we again want to verify this identity. They have this extra directive to manipulate each side of the equation independently. I'm going to mostly disregard that because that's exactly what we have been doing. That means to start with the left side or the right side. Start with one side and manipulate it to show that you get the other side. If we're not able to manipulate it to get the right side, what this directive tells us to do is that, say we can simplify this down to get something here. We could then take the right side, simplify it down, and if these two things are the same, then we're done. We've shown that the left side is equal to the right side. So let's see. When I look at this expression on the left side, I notice that in the numerator, I can factor out a sine, which leaves me with 1 minus sine squared x. At this point, I hope that 1 minus sine squared x is making you think of a Pythagorean identity, because we see 1 in a squared trig function. If cosine squared plus sine squared is equal to 1, 1 minus sine squared is equal to cosine squared. So what's happening in green is I am using a Pythagorean identity to replace 1 minus sine squared. Now I can cancel these cosine squareds, and I've showed that the left side of the equation is equal to sine x. Now let's work with the right side of the equation, which is sine squared multiplied by secant over tangent. Let's switch everything to sine and cosine and see if we can cancel out anything to also get sine on this side. So I've switched the secant to 1 over cosine, and I'm going to switch the tangent to sine over cosine. Let's clean up in the numerator. The sine squared is sine squared over 1. So we'll multiply those fractions in the numerator straight across the top. In the denominator, I still have sine over cosine. We'll keep change flip because we are dividing fractions. And when we do that, we see that the cosines cancel, one of the sines cancel, and we're left with sine x. So because we get the same thing from manipulating both sides of the equation independently, we have established that identity. In our last two examples, we are going to be rewriting algebraic expressions in terms of theta. So in problems like these, I'm going to give you an algebraic expression, and I'm going to give you a substitution. We will always be working in the first quadrant for these problems just to make sure that we're not violating any domain issues. And when we apply the substitution that I give, for instance, I've said here that x is 4 sine theta. So instead of x squared, I'm going to put 4 sine theta squared. Let's simplify this. So we have 16 minus, we need to square the 4, and we also need to square the sine. So we have 16 minus 16 sine squared theta. We can factor out a 16, because both of those terms have a 16, leaving us with 1 minus sine squared. We can continue to simplify this because 1 minus sine squared is cosine squared. And then the square root of 16 cosine squared is 4 cosine theta. And I know it's positive because theta is in the first quadrant. Now let's look at example 12. We're given the substitution here. Let's substitute this in. So I have 3 tan theta squared plus 9, all under the square root, and that's divided by x, which is 3 tan theta. Let's square the 3 and square the tan. So you'll notice a theme in problems like these that we should always be able to factor something out under that square root. Notice how here I'm factoring out the 9. And when I do that, I should be left with an expression that I can apply a Pythagorean identity to. So I have not done anything with this tan squared plus 1 yet. But if we go up and look at our identities, we see that tan squared plus 1 is equal to secant squared. So I'm going to replace that with secant squared. And now we can actually apply the square root and be left with 3 secant theta over 3 tan theta. The 3's cancel. I'll rewrite secant as 1 over cosine, and I'll rewrite tangent as sine over cosine. And then we'll keep change flip to see that our cosines cancel out, and we're left with 1 over sine theta, which is the same thing as cosecant theta.